Hello and welcome to another video. In this lesson, we'll be focusing on the dot product, also known as the scalar product, which states that vector A dot vector B equals the magnitude of vector A times the magnitude of vector B times cosine theta. However, this is the geometric definition of the dot product. There is also an algebraic definition of the dot product, and this definition will prove to be as useful as the geometric definition is in physics. So we want to prove in this video that the dot product of vectors A and B has to equal the sum of the product of the components of vectors A and B. This should be an equivalent statement to the geometric definition we stated above. And let's not forget that n denotes the number of dimensions we are dealing with when breaking down the vectors into their corresponding components. Now, let's set up our problem. We have one vector, which we will label vector B, another vector, which we will label vector A. The angle that separates the two vectors will be labeled theta. A third vector that connects the two vectors will be labeled C. We then have our Y and our X. So let's just label X and Y. We define C to be the vector that connects the tips of vectors A and B. This is because we need vectors A, B, and C to form a triangle. We do this mathematically by defining C as the vector that needs to be added to B to get A. Consequently, C is equal to the difference between vectors A and B. Before we can continue, we need to declare some statements. First, we will need the law of cosines. If you're unfamiliar with this law, go to a video on it linked in the description below. This law states c squared equals a squared plus b squared minus 2ab cosine theta. Second, we will need the definition of the magnitude of a vector, which is the square root of the x component squared plus the y component squared plus the z component squared plus ... However, we can also define this more generally as the square root of the sum from 1 to n of the squares of the components of the vector. Lastly, we need to utilize the fact that the component of a resultant vector equals the sum or difference of the corresponding components of the original vectors, which in this case would mean Ci equals Ai minus Bi. Now, let's tackle the problem. Since vectors A, B, and C form a triangle, from the law of cosines, we know that the magnitude of vector C squared equals the magnitude of vector A squared plus the magnitude of vector B squared minus 2ab cosine theta. Rewriting this, we get 2 times A times B cosine theta equals the magnitude of vector A squared plus the magnitude of vector B squared minus the magnitude of vector C squared. Now we can see that this equation contains the geometric definition of the dot product. So, by substituting the dot product and the definition of C, we get 2 times the dot product of vectors A and B equal A squared plus B squared minus the square difference between vectors A and B. Dividing both sides by 2, we get the dot product of A and B equals 1/2 of A squared plus B squared minus the square difference between vectors A and B. We now replace the magnitude of the vectors with their component representations. So we have 1/2 square root of the sum of the components of A squared plus the square root of the sum of the components of B squared minus the square root of the sum of the difference of the corresponding components between A and B squared. Canceling out the square roots and squares and distributing the squared term within the third sum, the expression for the dot product becomes 1/2 the sum from 1 to n of AI squared plus the sum from 1 to n of BI squared minus the sum from 1 to n of AI squared minus 2AI times BI plus BI squared. Now, splitting the third sum, we get 1/2 the sum of AI squared plus the sum of BI squared minus the sum of AI squared minus the sum of minus 2AI times BI squared, and finally minus the sum of BI squared. Now we can clearly see that this term cancels out with that term, and this term cancels out with that term. After canceling out the sums, we are left with 1/2 of the minus sum from 1 to n of minus 2AI times BI. Moving out the constants, we're left with minus 1/2 times minus 2 times the sum from 1 to n of AI BI. And for our last step, the dot product of vectors A and B equals the sum of the products of the components of vectors A and B. Thank you for watching. If you like this video, hit that like button. If you have any comments, questions, or concerns, leave them below. Remember to click that subscribe button, and as always, see you next time.